One of the functional groups we talked about in the previous section was alkenes. Alkenes are hydrocarbons that contain a carbon-carbon double bond. And we name them similar to alkanes, which are all carbons and hydrogen single bonds, but we use the suffix ene instead of ane. We normally indicate the position of the double bond with a number. So for example, if we had the following alkene, this is a 4-carbon chain, and as we count along the chain, the double bond starts at the 2 position. So it's between carbons 2 and 3. And so we say that this is 2-butene. Or we say it's but-2-ene. Where the 2 indicates the position of the alkene along the chain, and the ene indicates that you have a double bond. Now this is different than, say, that alkene, which has the double bond on the 1 position along the chain, and so this would be just simply butene. Or if you wanted to say 1-butene, that would be okay. And when substituents are placed along the chain, the priority rules still must be followed. So alkenes are higher priority than halides, but lower priority than alcohols, for example. So if we had the following structure, this would be a 6-bromo 1-hexene. In this structure would be a 5-methyl hex 4-ene 1-ol. And we say that the suffix is ol because that's the highest priority functional group in this molecule. There are 3 other groups that contain a carbon-carbon double bond which have common names, so we'll go over those right now. The first is the vinyl group. So a vinyl group is just a double bond that's hanging off of a chain. This is known as a vinyl group. So the common name for that molecule would be vinyl bromide. The next common group is this one, which is a CH2 followed by a double bond, and this is known as the allyl group. And this molecule here would be allyl bromide. And the last group is this one, which kind of has a branched system, and we know from the isopropyl group that it has the prefix iso, meaning branched. This is an isopropenyl group, indicating that you have a double bond on one of those branches, and so the molecule that has a bromine substituted would be known as isopropenyl bromide. And these are common names for functional groups that contain double bonds. Now, how do we name double bonds for IUPAC nomenclature? Well, it's similar to what we just described before, where you have in the examples on the bottom, 6-bromo 1-hexene, or 5-methyl hex 4-ene 1-ol. But there's one additional piece of information, and that's when you have multiple groups on either side of an alkene. And so this is where we get into a convention known as E and Z nomenclature. The E and Z nomenclature of alkenes is also known as the Cahn-Ingold Prelog convention, and it dictates that we assign priority to the various groups attached to the alkene in order to distinguish between the isomers. So the E alkene, or prefix E, comes from the German word entgegen for opposite, and it's to indicate that two highest priority groups exist on opposite sides of the alkene. Whereas the Z isomer, Z stands for the German word for same, or zusammen. This indicates that the two highest priority groups lie on the same side of the alkene. And the E and Z system of nomenclature assigns priority based upon atomic number. And so there are several rules that we have to follow. The first is that atoms directly attached to the alkene are assigned priority based on their decreasing atomic number. So the higher atomic number is higher priority. Now, if two groups have the same atomic number, you consider atomic mass. So groups that have the same atomic number but higher atomic mass are going to be higher priority. If those two are the same, if two groups have the same atomic number and the same atomic mass, you have to move along the chain to a different atom. Until there's a difference in priority. The fourth rule is that if two groups have the same atomic number and the same atomic mass and lie in the same position along the chain, but one of them is doubly bonded, then you count that atom twice. All right, so if above is the same, you count double bonds or triple bonds multiple times. All right, so let's say you arrive at an oxygen along the chain, but one of them is only singly bonded while the other is doubly bonded. The one that's doubly bonded will count twice. It's as if an atom were attached to two oxygen atoms because it has two bonds. But you have to be careful, this is not additive, so you can't add the atomic numbers of two oxygen atoms. It's just simply that it's doubly bonded. And the final rule states that if the two highest priority groups are on the same side, we say that's Z. If they're on opposite sides, we say that those are E isomers. And this designation goes before the entire name. And so you would have a Z alkene or an E alkene. Now note that we don't use the terms cis and trans when naming alkenes. We only do this because the E and Z nomenclatures are IUPAC conventions. Cis and trans are used only when indicating the relative positions of the groups. So we can talk about them about two groups being cis or trans to one another, but when we name them using IUPAC nomenclature, we have to use Z and E designations. So let's do a couple of examples. So let's say we have the following alkene. The first thing we do is we look to see where the alkene is, and we designate the two carbons of the alkene. Now each of those two carbons should be treated one by one, so let me label them with a different color. Let's treat the red carbon first. On that red carbon we have a methyl group, so that's a carbon atom that's directly attached to the double bond, and then we have a hydrogen atom that's directly attached to the double bond. In this particular case, carbon has an atomic number of 6, while hydrogen has an atomic number of 1, and so the methyl group is higher priority, so I'm going to circle it. Now for the blue carbon, I'm taking a look at the atoms that are directly attached to that blue carbon, and I have carbon atoms in each case. I have a carbon atom there and a carbon atom there. Well, that's the same atomic mass, and so we have to move along down the chain. The next thing we consider is the same atomic, first is atomic number, then atomic mass. We don't have any isotopes here. And so we move along the chain, and now we have an oxygen and a fluorine. Well, this first one here is got 3 bonds to oxygen, a double bond and a single bond, but the fluorine is only single bonded. Now, if you recall what I said before is that when you have double and triple bonds, you count those as if they're bonded twice or 3 times to a particular atom, but it's not additive. So you're still just dealing with a single oxygen in terms of the atomic number. So oxygen's atomic number is 8, but fluorine's atomic number is 9. And so fluorine is the one that is higher atomic number, even though that top orange carbon is bound to 3 different oxygen atoms. 3 different oxygen atoms is not higher priority than a single fluorine because it's based upon atomic number. And so these groups are on the same side, and so this would be an example of a Z alkene. Another example would be this one. Okay, in this case we have that red carbon atom has a methyl group and a hydrogen, and again the methyl group is going to be higher priority. On the blue carbon we have 2 carbon atoms that it's connected to, so we have to move along further down the chain, and now we get to oxygens in either case, but in this time the top orange carbon atom is bound to 3 oxygens, while the bottom orange carbon is only bound to 1 oxygen. And so in this case, the atomic number is the same, but the number of oxygens it's attached to is higher, so that makes the top carbon higher priority, and so this now is an E alkene. They're on opposite sides. Another example would be this one. So we have the red carbon again. Red carbon still has a methyl and a hydrogen, so that's going to be higher priority for methyl. And now we have a hydrogen and a deuterium on the blue carbon. And this is a case where there's a difference in atomic mass. Both hydrogen and deuterium have the same atomic number, but deuterium has an extra neutron. And so it's going to be higher priority because the atomic mass is 2 instead of 1, and so this is going to be an E alkene. And this is important when naming lots of different types of molecules. Here's just an example of a molecule that has a common name, but we still use the E and Z nomenclature. In this example, the two highest priority groups are going to be that methyl and that carboxylic acid. This is known as E-tiglic acid. The other stereoisomer is going to be this one, and in this case the methyl and the carboxylic acid are on the same side, and this is known as Z-angelic acid. All right, and of course as you have these groups on opposite sides of that double bond, these are known as stereoisomers. They have the same constitution, but a different orientation in space. Now these stereoisomers that arise from a difference in E and Z for alkenes are a specific type of stereoisomer known as a geometric isomer. So stereoisomer is sort of the bigger umbrella, and underneath stereoisomer is a smaller umbrella called geometric isomers. And this geometric isomer class is a class of stereoisomers known as diastereomers. And we'll get to that term diastereomer in the next chapter on stereochemistry. Now these geometric isomers, these diastereomers, do not have the same physical properties because they have different energies. And we can see that actually in the isomers of butene. So let's take a look at butene. And so butene has the following two isomers. We have an E-butene. This is E2-butene. But we also have the Z version, Z2-butene. These are different molecules. They are geometric isomers of one another, but they are indeed different molecules, and they have different physical properties because they have different energies. It turns out that the E isomer is about 0.7 kcals per mole more stable. And the reason why this is more stable is because it has those two methyl groups on opposite sides of that double bond. And so in the Z2-butene, you have a van der Waals interaction when those two methyl groups come into close contact with one another. And those two methyl groups are lying cis along that double bond. This increases the steric strain of the molecule ever so slightly that it's higher in energy. It drives up the energy of that cis isomer. Another way of depicting this is if we were to draw out the hydrogen atoms of that methyl group. So let's do that. We see, just like in the case of conformational analysis, when we have the nuclei of two atoms overlapping, that gives rise to an increase in steric strain.